So welcome to this first video, very first video, on boats and our robot boat pioneer project. So in this one, I want to give basically an overview of the architecture of the electronics and software platform that sits behind all the boats. This is something that's evolved over the last couple of years from very humble beginnings to now a fairly decent platform that supports our little fleet of boats, in fact. Um, as a core principle, we've kept it very modular and extensible. So as each new design iteration comes along, the platform can fairly quickly be tweaked to support whatever it is we want to do. So let me start with a sort of an architecture diagram, because who doesn't love an architecture diagram? So in this view, this is the same view that's up on the blog post up on the website if you want to read along later. But there's three kind of main architectural components overall. So we've got the boats themselves, which I'll talk through first. We've got the means of communicating with the boats, so various types of telemetry and networking. And then we have a central control and management system so that we can keep an eye on what the boats are doing. We can record log data and analyze things after the event. So if I start with the boats themselves. So for the simpler devices, if you take our very first boats, which were the paddles, so very simple tank steering paddle boats, they didn't need a great number of sensors or controllers. So they had a motor control, dual channel motor controller for the paddle wheels. They had a GPS compass, stuff like that. Fairly straightforward. Everything is easily contained on one microcontroller with a bunch of connections. Some of the more sophisticated boats, so particularly the main wing sail test boat we have now, Easy Sailor, that has two microcontrollers. So there's one in the hull that takes care of all the hull stuff, and that also manages navigation and so on. But there's a second microcontroller in the wing that has a bunch of additional sensors and manages the wing tail position. They're both separate microcontrollers. They both think they're actually completely separate entities and they communicate over the radio network. So in that sense, the platform is flexible enough that we can have, I guess, logical systems made up of a number of different controlled nodes, all using the common platform. So what that platform is made up of is an ESP32 based motherboard. Selected the ESP32 fairly early on as the processor of choice. Mostly because it happens to be my favorite processor of choice these days for developing embedded stuff. I've experimented with most of them over the years, but the ESP32 is an excellent blend of cost performance. It's got built-in Wi-Fi, Bluetooth. It's got fairly decent I/O support, not a huge number of I/O pins, but enough. It's got I2C, SPI we use that for radio comms and SD cards and stuff. Yeah, we don't really use the analog, but it's got analog inputs if you need it, and a bunch of digital I/O. It's also got a very fast dual processor. I think it clocks at 240 megahertz, a fair amount of flash, and a lot of memory, so RAM, which is great for doing these sort of more complex applications, which the boat project definitely is. On top of that firmware, that sort of base microcontroller then, the motherboards that we've developed, they started off as basic carriers and are now quite a bit more sophisticated. So they have a number of integrated devices. If I find a picture of one on the screen, what this one will do, you can kind of see in the background here. So this is one of the slightly newer boards. So we've got the ESP dev kit module at the moment. The next version of the motherboard will have the ESP32 module integrated on board. We've got an I2C multiplexer on here that gives us 8 different independent channels of ITC. I'll talk about why in a later video. Simple things like a status neopixel, so we can debug what the hell's going on, very basic level. We have an onboard magnetic compass, so the boat can get orientation. Hiding behind the scenes under here is an RFM69HW mesh radio module. And then we also have an onboard GPS for which you can see the antenna sticking out the side here. The back side of the board you can't quite see then has the power inputs, a bunch of other I/O pins that are exposed along with power for connecting devices like servos, and an micro SD module on the back. So that board forms the basis of most of the fleet of boats at this time. but it's complemented then by a power modulator on the side here. This simply outputs 5-volt regulated power for the motherboard and other devices, but it also includes a 3-channel current sensing unit, so we can monitor battery voltages, power levels, yeah, and do handy things like prompt us when the boat's running low on power and we should bring the damn thing back again. So that's kind of all the key bits in the motherboard with the power module. All of the boats then have one consistent firmware. So major design choice early on. I didn't want to have multiple different compiled pieces of code for different boats. A couple of reasons for that. One is, as a project team, we're not all software developers. So don't really want to have everyone in the team needing to run a full development environment every time we tweak something on the boat. Second thing is, a lot of the tweaking that we do is configuration. So tweaking things like servo set points or waypoint headings, lots of stuff like this is not really stuff that I think should be buried in code. This should all be user configurable stuff that we can do at runtime without having to fire up a development environment. The other reason for this is I wanted to keep a really clean separation between kind of the complexity that's buried in the firmware itself versus exposing a much simpler interface for, I guess, us as the users, particularly when we're lakeside or seaside. Don't want to be hacking around in code at that point. We want to be using a much friendlier interface, something that's less error prone and more robust. So the firmware tries to hide a lot of the complexity and instead exposes a much simplified set of logical modules. Those modules either represent physical devices like sensors or actuators, or they represent logical computing nodes. Things like there's a navigation module that takes care of managing a set of waypoints. There's a sailor module which takes care of how to sail. So it deals with things like attacking algorithm and choosing an appropriate heading relative to the wind. There are others that take care of, there's one called turn rate, which manages a PID loop for maintaining heading using an output actuator like a servo. So we try and encapsulate functionality in fairly simple modules. They can then each be developed, tested, and used across multiple devices. What the configuration file for each node then does is say, what combination of modules do you want to instance or activate for that device, and how do you want to connect them together in terms of inputs and outputs? That's equivalent to, say, a simple node-based like programming language. Yeah, there's many of those. So much simpler than writing code itself. And we can expose that through, although it's in a configuration file, we can expose that through a user interface when it comes to runtime. So that's the control setup for each node. We've then got the mesh networking transports, as it says here. So fundamental challenge is we want to be able to talk to the boats. Say talk, obviously by a computer. We want to be able to monitor the boats with telemetry data over a number of different radio links. So when we're very close, or even on a workbench or doing testing, Wi-Fi is pretty handy. It's fast, it's got a high bit rate, etc. When we're a little bit further away, say up to a couple of 100 meters, we want to use relatively short range radio links, which are still fairly high data rate, easy to use, cheap. And for that, we use the RFM 69 HW modules. For the initial wave of motherboards in development, they're all on 915 megahertz. We're then currently exploring using 433 megahertz to get a bit more range out of them and sacrifice some data rate. We'll see how that goes. As things get further away, we then want to switch to different radio techniques. So one option not yet explored in detail is using GSM network, as that can get quite a long way offshore when we get to ocean testing. And then when it's even further offshore, we'll switch to Iridium satellite link, which we've tested, but it's not yet fully integrated to the overall networking system. Now, so there's a bunch of different transports we want to use, but we want that to be seamless. Don't want kind of dedicated networking for each interface or having to manually switch. Sort of implemented on top of the transports is a custom mesh networking protocol based on the Babel routing algorithm with a bunch of extensions. What that does is each node in the network acts as a router for everything else, They form a dynamic topology, so they each build a routing map basically of how to get to all other nodes. They'll do store and forward and reliable delivery of packets across the network, um, which is super handy when we're out in the field. So if we've got a poor radio link to a boat out in the lake, we can chuck another boat in the water and use it as an intermediate network relay. Um, yeah, if one particular connection fails for any reason, it will automatically switch to another one, and all the other good benefits of the mesh network. So that's, yeah, it took quite a while to test and get that working robustly, but now it does. It's a kind of super fundamental and extremely useful part of the overall platform. And then what that allows us to do is not just the individual nodes to talk to each other, but also then to talk back to a central management server. So the combination here is we have a Node.js based server, which takes care of communications. So that talks all the same mesh networking protocol that the nodes talk. It also does some data logging and network diagnostic stuff. It also then hosts a web-based UI. So it's quite nice, at least. The server and the web UI all use the same JavaScript libraries on the back end, so things only have to write one set of code. The web UI then has become quite sophisticated. So that allows us to track what's happening with the boats. And I'll give you a mini demo of that in a second. We have then one more component of the system, which is we want to be able to log any activity while we're at the lake to somewhere central, so we can later play it back, analyze it, discuss what's happened. And for that, we use a cloud storage service, Firebase storage. So that stores not only log data, but it also backs up all the configuration files and settings for the various devices, and a few other bits and pieces, which is quite nice when we're working off multiple laptops, typically at the lakeside, or we've got various computers on benches. All of those can be running the same server software. We can all read off the same file cloud storage service. It also, because it's quite lightweight, the server instance, it will run happily on a Raspberry Pi. So kind of thinking ahead when we get to longer endurance missions and we want to run a server potentially days or weeks, we can run a low-powered Raspberry Pi device on site rather than having to have a high-powered laptop or workstation, whatever. So that's the overall components of the architecture. This is a screenshot of the web UI in action. So what we've got here on the left-hand side are all of the nodes in the network. These are the ones that the server's seen, and it stores a reference to those in the cloud for future reference. When you've selected a node on the right-hand side, then it builds a UI out of the modules that particular node is running. So there's a discovery process that runs in the background and enumerates what modules are loaded on the device, reads off any parameters they're exposing. So in this case, well, a whole bunch of modules. The management module is common to all nodes. That allows us to do things like remote reboot, tells us the uptime, that sort of stuff. RFM69 is the main radio telemetry module, so that's telling us the signal strength, packets sent, received, data rates. UDP is the UDP Wi-Fi based telemetry module. We've got the onboard power sensor that's telling us the local battery or cell voltage of the LiPos. We've got GPS as a compass down here. Term rates managing the rudder control. We've got the rudder servo here, and this is basically a mapping control, so that we can fine tune the output response of the servo. So it uses a Bezier control curve, which is quite useful. We've got a wind sensor on board that's also doing a bit of histogram mapping, so we can see average wind location, and waypoint module down here feeds a sequence of waypoints to a nav module we can't quite see. So this is fairly typical for one of the boats. In this case, it's the hull of the Easy Sailor, and then there's a second module for the wing. In fact, if I switch to a slightly more live view, we can see the other modules down here. So we also had the nav module that takes care of how to get to a waypoint, and the sailor module that takes care of how to sail. If we went to the wing, that's then the complement. So this has got the wing trim servo, same sort of power stuff, but except this one's also got an IMU sensor, so we can monitor the orientation of the wing, basically look at how much heel the boat's going through. Some of the other views, so for every node we've also got the ability to have a custom visualization that's unique to that particular node. So the way this works is there's a little JavaScript file behind the scenes, which just defines how to generate the visualization for that particular device. This allows us to pull quite a lot of information into one view and tailor it to that particular node, which is very useful for different styles of device. We've got the file system access, so we can look at the backup of the files that are stored up in the cloud, or we can look at the local file system on the node. So here you can see this is the configuration file for this particular device. Very simple INI file format. So what's the address of the node, and then an INI section for each module to load. So what's the type of the module and what ID to give it, and then any parameters to configure that module. So very straightforward. You can also have other custom things. So in this case, we have a waypoint file, which we can visualize over here. So in this case, Easy Sailor was set up to head out to waypoint 1, then to waypoint 2, waypoint 3, and then loop around them. Added a few bits to the editor, so if you select a line in the file, it will highlight that node, and if you drag and drop around here, it'll update the line. So nice and easy to edit waypoints. You can then send that back to the node, assuming it was online. We've also got making sure we get our configuration files correct. We've got a network view of how the different modules on the device are configured. So in this case, let's go to something simple. So the GPS module is outputting a location value, which is sent to the waypoint module. That allows it to track how close we are to a target. The target and our current location are sent to the nav module. That then generates critically a heading that we should sail on. Gives that to the sailor module. That then works out what to do with it and selects an appropriate course. So how to tack. Tells turn rate, that's the target heading you should be on, and it measures the actual heading from the compass module. That then goes through a receiver one that allows us to basically intercept the command from a radio control receiver and take over if we want to. And then finally, that command gets to the rudder servo and it actually steers. So this kind of thing allows us to just check we've got everything configured correctly, we haven't missed a connection or anything else. Yeah, last one, that's not really very exciting. So that's sort of the per node settings. In the map view, then you get the node itself. If it's got a wind sensor, then it will give us the local wind direction. If it's got a compass, it will give us the heading in terms of which direction the arrow is going. And if it's moving, we'll get a snail trail. So if I switch to some log data from a little while ago, let's jump into here somewhere. And then let's skip it a little bit, see if we, so here we go. As we start to get, it'll replay in real time, or on the time base that things were happening when we recorded the log data. So if there's pauses in the log data, so here you're seeing it's quite a slow packet rate because we were we needed to move the radio base station on land a bit closer to the shore to get the signal. But here you can see it starts to build up the snail trail of the GPS points as it's received. You can see the incident wind direction moving around, the orientation moving. And if we went to the visualization view, you'd see the same data brought through here. So what's the local orientation of the boat? Where does it think the rudder should be? Where does it think the wing sail should be? How far to the next waypoint? All this sort of stuff. If we've got online nodes, then they'll come up like this. So you'll get a bit of extra data. This is a device just sat on the bench that I had on a few minutes ago. Yeah, and then you get a live view. The last two bits, if I plug this node back in so we get some live data again. The last couple of diagnostic views, we have a network topology view. So this allows us to debug the mesh network. So for this, and any node that's selected, it'll just run a constant trace route, so we can verify the outbound and return route to any packets to that particular node. Node 250 in this case is the server instance. Node 2 is the actual physical device. Yeah, so we're getting pretty decent ping time. So the round trip is what, 30 milliseconds. It's going directly out and back as you'd fully expect. We can see a little bit here, this little bar graph on each node. This is the local packet queue. So essentially how busy is the router, the local router on that device relative to its peak capacity. And then we've got some link metric information as well. This gets quite complex when you've got a whole bunch of nodes running. The last stage of this to help us debug is a histogram of all the different packets that are flowing across the network. So we can check basically, is the network getting saturated or behaving appropriately in terms of packet prioritization. There is automatic throttling based on packet priorities built into the way the mesh networking layer works. And this is part of debugging that's all working properly. So that is the server instance. And that concludes this little intro. So I think in future videos, I'll go into the motherboard electronics and the software architecture in a bit more detail. Talk about the module structure and some of the specific modules. Things like how does the Sailor module, actual work, how does the tacking algorithm work, all that sort of stuff. But this hopefully gives a decent overview of the system components. Yeah, might give you a flavour for what to dig into next. Hope that's useful.